Welcome to Data Skeptic Machine Intelligence, our podcast series exploring contemporary topics in artificial general intelligence and large language models. We've had a good little run of episodes lately asking questions about how ChatGPT and other large language models perform in other domains. We've heard they do well at coding. They do well when describing graphs and networks. And today we're going to find out about their ability to do math problems. Now, something you might know, and it's easy to go and check for yourself, the current state of large language models are surprisingly bad at mathematics. Now, I know it's not going to be like that forever. Give it a few years and I'm sure, some kind of way, LLMs will also be reliable calculators. And today's interview might just give us a hint as to how those goals can get accomplished.
I'm Aman. I'm a PhD student at Language Technologies Institute at CMU. I'm in my final year, and I do a lot of large language model stuff, reasoning with large language models, code generation, things like that.
Hi, I'm Shuyan. I'm also a final year PhD student at the Language Technologies Institute at Carnegie Mellon University. I work on building agents that can help us to solve complex tasks by a simple natural language command.
Well, NLP has certainly changed a lot, even in the time you've both been studying. Can you share a few thoughts on the journey?
I always wanted to do language generation, and that's language generation and common sense reasoning. So that's basically what I've been doing. But like you point out, things completely changed after large language models. I have a very concrete example. So my first paper in my PhD was on politeness transfer. So you're given a sentence and you want to make it polite. I mean, today there's no need to do anything. You go to ChatGPT and just ask to make it polite. But back then, it was non-trivial. We had like a couple of models. We had a special data set. We had a new modeling paradigm we called tag and generate. It was a paper. It made a lot of news. And I think clearly a lot of that is not needed anymore, right? So it's kind of super cool to see how doing even very difficult things is now very easy. But again, I think to be a bit more cautious and pragmatic, I don't think we are at a point where we can say NLP is solved or reasoning is solved. I think there's many challenges which become apparent as you start playing with any non-trivial data set. So it has definitely evolved and it's been awesome to see the change, but I think lots of challenges still.
Yeah, I guess for me, the most impressive thing is like we start to testing on more and more realistic scenarios. So when I start working on code generation, we start with just generating like a one-liner, which is just have one line of code. It was challenging. Back to then, we need a lot of like syntax-aware encoding to make sure the grammar is correct. We have to augment a lot of data and train like a small-scale model. But right now, a lot of techniques are simplified, but the outcome is even better. Now we can not only do just simple like single one-liner code generation. We can do function level, class level, even repository level right now. So I think basically the application is broader and actually the underlying technique is simpler. So that is the most fantastic thing for me.
I've had some good success myself generating code using an LLM, but maybe it's the limit of my imagination, but I only seem to get good things where I ask like maybe 30 lines, like here's this function, or can you improve what I already have? Do you think we're hitting ceilings like that, or can it really the sky's the limit here?
Oh, yeah. So when I say we can generate like a repository level code, I just mean we are starting to get into that point, getting more focus on that specific scenario with like more and more evaluation data set. But of course, performance is not there yet. But I don't feel like we are hitting a ceiling there for a couple of reasons. I guess maybe, for example, we have like right now we have longer context support decoder models, and we can do a lot of retrieval. I think maybe right now a lot of pre-training are still not that like repository aware, but like if we can also incorporate those to our pre-training and like instruction fine-tuning, I think we can get even better performance. It's just a starting point.
I agree with Shuyan, and I think it's also a function of how common or how popular the thing is that you're trying to do. We have a paper called Self-Refine for which I built a demo in React, and I don't know any React, but basically by prompting GPT-4, I was able to sort of get it to do a decent demo. where you enter a string and it generates a nice graph and things like that. So I think those use cases are maybe common. So if you're doing something that lots of people have done and have discussed on Stack Overflow, maybe it can also do like longish code generation. But if you're doing something very specific, I think that's more of a problem.
I also have a similar experience. I did like a Flask app. I know Python, but I don't use Flask a lot. But I was able to do a little bit more interaction with the GPT-4, and I was able to set up my application up. And my friend told me it might take him 1 day to work on that project, but it was basically took me 3 hours to do that. Despite I need a little bit knowledge on how to do debugging, how to select the important part of the error message and then send back to the model.
Well, for as good as these language models are at code, they can be embarrassingly bad at some things like basic arithmetic sometimes. For listeners who haven't posed a lot of these problems to models, could you talk a little bit about some of the limits you've seen in that domain?
The most common example that anyone can try right away is to take two 3-digit numbers and try multiplying them with GPT-4. There's a good chance that it'll fail. Problems like that, the models do struggle at, even models like GPT-4. That's kind of interesting, and I think you can make argument both ways. So we have a paper with some of our co-authors on how do you fix these problems, but I guess we can come to it later. There's a very surprising failure mode in multiplication, but also in like adding very large numbers. In some sense, that's obvious because it's like you don't have many examples of all kinds of multiplications, and at the end of the day, the models are doing some sort of learning from the corpus. So if you have not shown it enough examples, like why do we expect it to pick it up? But then it can do all these crazy things. So I think the answer is a bit more nuanced.
Would you be able to describe one of the questions? If you have one handy, you could read it out loud or just make one up so we get a sense of what the challenge is. What are some of these problems?
Okay. Yeah, we have some here. John decides to take up an odd hobby of speed talking. His normal speaking speed is 150 words per minute. After training, his speed is 2.5 times faster than his starting speed. How long would it take him to speak 10 pages if each page has 450 words per page?
I need a pencil, but I can solve it. Yeah.
Yeah. But I think like the math data set that I was talking about, I also got hold of the paper. And the numbers there are 50% solve rate if you use text and 70% solve rate if you use PAL. That's a crazy jump, I think.
A very optimistic person might say we should just make the large language model bigger, double the parameters, and somewhere along the way it's going to learn arithmetic too. Your approach is different. Can you describe what program-aided language models are?
Yeah, so I think the idea is basically when we are solving a problem or something like a math problem, there are two things. The first thing is what has to be done, and the second thing is how to do it. For example, if the question is Shuyan and Aman have 2 apples each, how many apples do they have? Then knowing what has to be done is that you have to take the number of apples that Aman and Shuyan have, which is 2 apples each, and then calculate 2 plus 2. And then the second part is actually doing the calculation. What we observe in programmatic language models is that you don't really have to force the language model to do everything. You can only make it generate the plan on how to solve the problem. Because these models are trained on tons of Python code, Python is also very natural. Maybe, let's generate a Python program to solve the answer and then not bother the language model with doing the calculation, but send the program to a Python runtime to get the answer. So this kind of division of what has to be done and how to do it, and our way of doing it is with a program, and it works pretty well. So that's the idea.
So I could load up ChatGPT or some other large language model. I could pose a question to it, and then I could add to my prompt, instead of answering this question directly, please give me a Python program that will get me the answer. Is that basically the approach, or is there more engineering to it?
Yeah, I think it's basically what they are talking about. And right now, they even have code interpreter. And for example, for BART, they have implicit code execution. Then you don't even have to say you need a Python program for that. Maybe they have some internal technologies to route to a specific generating of code.
Well, then as a technique, you want to have some measure of success. What can you use as a baseline to decide if your approach is doing a good job or not?
We basically compare with different prompting mechanisms, like you can directly ask the model to generate answer without the intermediate reasoning steps. And also we can use train of thought, which elaborate what are the intermediate reasoning before it get the answer. So we compare with both of them in many data sets in Big Bench Heart and like others. And we found Pound is better on those.
Well, it could be that the large language model would make coding mistakes, reference the wrong variable, have the wrong constant or something. Why is it that moving from language to this intermediary somehow allows you to get correct answers?
Yeah, I think so. There are two kinds of mistakes. One is syntactic and one is semantic. So syntactic are, maybe the Python syntax is wrong. And we see that that happens almost never. So it's like less than 1% of the times on GSM 8K that happens. So that's taken care of because we have a really good language model of code. The second problem that could happen is the more serious problem, which is semantic issues. And they do happen. The success rate is still not 100%. But I think the reason why it's much better than doing text only is there's two reasons. One is that we do absolutely no calculation. So all of those errors go away. So there's no addition, multiplication, taking log or anything. That's all routed to the Python interpreter. So that would be the biggest source of reduction of errors, right? So even if the model does not know what's 2 plus 2, that's completely fine, as long as it can say return a plus b or return 2 plus 2. And then we call up a runtime. And a second thing we noticed is that, at least for the problems we consider in PAL, it's actually very natural to represent the solution as code. So, the first step is create an init block where you initialize all the variables. The next step is create a nice flow. So, what's the first step, what's the second step, what's the third step? And I think that's kind of also a very natural representation for solving these problems. Not having to do arithmetic calculations is the biggest source of gains.
Yeah, I just want to add something about the second point as well. You're right, like models can still make mistakes on code, but I want to say like code is kind of also it can preserve the richness of the natural language by having meaningful variable name and the comments. So in that sense, we can see there's probably a smoother translation between the natural language and the code.
Thanks to our newest sponsor, math.fashion. Yes, that is a real URL. Visit math.fashion and check out their line of mathematics-themed t-shirts. They sent me the Klein Bottle shirt, which is pretty stylish. I've gotten a few compliments about it, and each one is the opportunity to start a long conversation about two-dimensional manifolds. Get more math in your life, specifically on your body. Visit math.fashion. Well, you'd mentioned less than 1% of them have a syntactic error. I think that makes it a better programmer than I am. But what percentage of the generated programs give it the correct answer?
I think the accuracy rates on GSM 8K with ChatGPT are about 78, 79.
Yes.
Something, so 78 to 79% of the time, it's like the answer is right.
And could you frame that for us? Like, is that an impressive score? Is that probably state of the art? And, what a human score? How do we interpret that number?
I think if we use chain of thought prompting with text only, I think you would get about 73% or something. 72% with text only. So that's the gain over a text-based reasoning or chain of thought reasoning with the same underlying model. And these are all middle school math problems, so you can expect a reasonable human to solve all of them. I mean, the funny thing is that because this benchmark is so popular, or I don't know why, but GPT-4 was actually fine-tuned on this. So they sort of looked at this benchmark, and so GPT-4 gets 94% with PAL on the same benchmark, and COT or chain of thought gets 92%. There's some gains there as well, yeah.
But it's already contaminated.
Yeah, because they're trained. Yeah. So, yeah.
And I think you mentioned these are middle school math problems. Do you have any thoughts on how it would work if you push it towards high school and college level mathematics?
Yeah, I think there's a recent paper actually. There's another data set called Math. It's literally called Math. And that has, problems which are fancier, more advanced, high school problems. They include geometry, calculus, probability. And there's a paper, the name's skipping me, but I can share later. They use PAL and this idea of self-debug to push that benchmark to 87% or something in late 80s, and it's the state of the art. And I think the model, even fine-tuned models, are maybe in the 50s or 60s. So I think the general technique is much more efficient even for like more difficult problems. Yeah.
So I'm going to ask you kind of an unfair question, but if you'll kind of pretend to be futurists, or maybe you consider yourselves futurists, but how is this going to affect the future of math and like the way kids learn and how we get answers to problems?
I think one thing is like if we can use program as an intermediate step to generate a better solutions, which is actually more accurate in any other techniques, and we can do some back translation from the programs to some natural language and expand those to the kids so that they can understand how does that work. Mostly, I think the gain here will be we have a better, more accurate solution. Then that part can help the education, but like we still need some kind of translation back to natural language so that everyone, the kids, can still understand. And I think this can probably be kind of applicable to other like majors or classes as well, like maybe chemistry or even physics or something like that.
Yeah, I think in general, it's the idea that you can use these models to write good code is going to change a lot of things. Like if you take any of the basic CS classes, right, all of the assignments, I mean, I'm pretty sure GPT-4 can do a large chunk. Maybe not just because it's so good, but because these assignments have been online for a long time, and they test concepts which are very frequent. So I think maybe it's like a broader theme, but the whole idea of how do you test people's programming abilities has to be, we'll have to rethink it, because if you give someone a take home test, if they have access to GPT-4, it's like, I don't think you can really test anyone
Yeah.
because it's going to probably do it, right? So if it's easy,
Yet that person will have access to GPT-4 in their professional life. It's sort of like having a calculator for the test or not.
yeah, but I guess there's some value in learning how to perform addition subtraction before you get access to a calculator, right?
Good point.
It's a very subjective opinion. I don't know, but I hope that it's helpful, because we did our undergraduates in the pre-chat GPT era, so so I think we had to like do all of that by hand. Yeah. Yeah.
In the benchmark problems, the mathematics are kind of at face value. I mean, there could be a red herring number and things like that, but usually there's very little red herrings, right? Just kind of the details are there. It's not trying to trick anybody or distract anybody. Do you think that you'll be able to generalize to a more natural language, like a little bit too talkative and sharing a lot of natural details? Will the system be able to tell the difference and find the mathematics if they're not at face value?
There's a paper actually called Large Language Models Can Be Distracted by Irrelevant Context. And what they do is they insert random statements in the questions in these benchmarks, and the performance actually drops. I think it's a challenge, but then I saw a recent paper where all the authors did were they added a statement at the beginning that says ignore any irrelevant statements, and the performance sort of improves. So who knows, right? I mean, it's, yeah.
Yeah. And I think we can do, like, if we know there will be some distracting context, we can do a two-stage process, right? In the first stage, we say, okay, have the language model to like filter out irrelevant information, then do the problem solving.
Exactly.
Yeah, I'm pretty confident the
It'll
model can just remove all the irrelevant context if we are not doing that everything on a single pass.
Yeah.
Yeah.
Yeah, these things are pretty good at language stuff.
Yeah.
I think so.
Yeah, there are a lot of sometimes funny examples like that one. Ignore the irrelevant details, and that's all it took. But for the rigor of computer scientists, that does feel a bit hocus pocus. How much time do you spend on the tweaking of the prompts to be just so stories?
So I think at least for the Pound paper, we didn't spend a lot of time on tweaking actual prompts. We basically did the translation between the train of thought prompt to our program style reasoning. So basically, we didn't tweak to specific more program favorable reasoning, but we basically just copy the train of thought to our scenario. I think the kind of magic here is we sometimes need to interleave in between the comments and the code. And the other is we have to have meaningful variables. So you cannot say like A equal to 2 while the A is actually like the number of apples.
I think in general, it depends. I think sometimes the paper is just a new technique. So for CoCoGen, which was like year and a half ago now, basically had this idea. And in the paper, we try a bunch of prompts and we want to show it generally works. For PAL, it was a direct translation. I think in general, at least the works we do, not much time in like carefully crafting the prompt. Like we try to work on things where the first prompt sort of works. And if it does not, then maybe it's kind of boring to just yeah.
And funny thing I think is for CoCoGen, you actually try different variations. Actually, it doesn't provide significant improvements or something.
Exactly.
It's just like the format of programming is important. Then the actual how do you like tweak that specific prompt.
And I think there's always an argument actually that if you have a better prompt, the performance could be better, and I think that's true. But there's also some recent work that does automatic prompt discovery. So, you can outsource that work to the language model. So you can say, hey, this is what I care about, and this is my first prompt, and the performance is 20%. So the model can propose something else and say, okay, this is 21%. So I'm in the right direction. Let me keep writing in this direction. And after 50 iterations, you get a better prompt. I think in a few, maybe we'll have some techniques that can do that kind of stuff.
Yeah.
And is there any significance to selecting Python as the language to use?
The reason why we took Python was it was the most representative language in the pre-training corpus of Codex. People did multi-language human eval, and I think Python is still the best performing language there still for Codex. But basically the reason why we chose this was Python was the most powerful, like has the strongest performance with Codex.
And we also know Python more than we know any other language. So there's that.
It's much easier to write in general and also set up for executions.
Exactly. Yeah. You can quickly execute it. You don't have to like do a jar file and all that. So I've done enough of that. So I don't want
to share your thoughts there. Yeah. There has been somewhat of a trend in machine learning to make everything end to end. Like long ago translation, maybe you first wanted to extract the phonemes and then figure out what words were made up of the phonemes. And now you put the raw audio in and you get the translation out. Do you think maybe that trend will end if we're seeing like there's a benefit to offloading some of the more mechanical calculations like a logarithm to the Python interpreter?
I think it really depends on how large is the scale of the task. I think maybe some of the, especially like natural language processing task, we start from moving from more like modularized methodologies to more end-to-end methodology. As you say, like machine translation. We don't do a lot of computational linguistics methodology to discover some features before we do the end task. But if we are talking about even higher level task, like maybe solving a very complex problem, I think we still want to leverage different components, but which can be orchestrated by language model or whatever powerful model. But we still need to leverage the power of individual modules because they have their specialties. So in this way, we can achieve a better performance.
Along the same lines, I think there's also this question of, do we really have to express everything in language, and is everything really expressed most efficiently in language, and will everything be available in the pre-training data? I think the answer is no. And there's some obvious fail cases. For example, if you want to build a system that reasons about what happened today, unless you have a way to train a language model every hour, you really need to do some sort of retrieval to get the new piece of information and reason about it, right? So what's the stock price today? What's the weather like today? What should I do today? How do I get from where I am right now to this place I want to be at efficiently? You can still use a language model to solve these questions, but language models will need signals from the real world. They'll need signals from what's happening today. They'll need all that, maybe a different modality. And I think it's here to stay, this idea of using language model as some sort of an operating system and then building on top of it. Yeah.
And are there any other approaches you would contrast your approach against?
I think, prompting is kind of full of techniques, different ways of prompting. Chain of thought is one where before you spell out the answer, you make the model think about the answer. So, in this case, the chain of thought could be, okay, John's normal speed is 150 words per minute. After training, it's 2.5 times faster. So the new speed is 150 times 2.5. So the model sort of is thinking out loud, and it's thinking out loud in text. And in our approach, it's kind of writing a program. So that's kind of the most direct comparison. And I think that's our main sort of baseline, so to say.
And what's the future of the work? Where can it go next?
So for me, I'm trying to incorporate program, this kind of using program as an intermediate reasoning step to solve complex interactive decision-making tasks. Because I believe program is a good orchestrating. It can basically enhance the expressiveness of task solving. So let's say like here we basically say program can help a model to connect with tools like Python interpreter or even other APIs. But I think program is in general more expressive. So for example, people do planning. We try to decompose a high level task to subtask, which is more manageable. But like in the program world, it's basically writing nested functions, and those functions are reusable. So I make an analogy here, and also like we have situational variance. So for example, if I want to take something on the table, I just take it. But if I need to take something from the drawer, I have to open the drawer first. So in program, we can basically write this very concisely as a if-else control flow. So I think that there are a lot of analogy between like how people are solving tasks and how we can express that in programs. And apparently program is like we can connect to tools by simply import their APIs and probably read a little bit about their API documentations so that they can naturally adapt to those scenarios. So for me, I will try to make program useful in the more interactive decision, like solving complex interactive decision-making tasks.
And Aman, similar question for you. Where does your research lead next?
I think in terms of programming and generating programs, we have some work on learning to optimize programs and some work on what happens when you have programs that have silly bugs, which is there's a bug which is in one line and needs a change of one or two characters to fix. And I think in general, and I guess this is where I'm getting to some crazy ideas, which is not necessarily my research, but one idea that I'm very excited about. And you see sort of this coming up in the literature, but no one has really sort of, buckled up and sort of looked at it in detail, which is what happens if you start pre-training your language models from code. So you don't start pre-training with text. You have some sort of a small duration or some token, when I say some, of course, a few billion tokens of code before you start pre-training. There's work out there that shows like pieces of it. So there's work that shows that code in general has very small perplexity, which means that it's easier to predict. And that makes a lot of sense because, a lot of the times programs are predictable. If you have written a class and if you're completing the class, then after the init block, you already know all the variables. So the number of things that can come next are sort of reduced in a program. And of course, there are indentations and those things. So there's work that shows programs are easier to learn. They have low perplexity. And then there's work that shows that if you mix code with any other modality, then this observation holds. As you scale, the perplexity gets lower and lower. So I think an interesting hypothesis is that if you start training from code, is it the case that sort of gives a good initialization to the model? We have a reason to believe it. One more sort of hypothesis is that if you look at the OpenAI's descriptions of these models, the base model for lots of the GPT 3.5 series was actually Code Da Vinci 002, which is apparently a code generation model. Again, we don't know a lot of details for many of these things, but I think to me that's very interesting. Like, is there something fundamental about programs and code that can help us train good language models in general, like beyond code generation? I think that's something I'm very interested in. Yeah.
Well, we've touched mostly on the use of large language models to solve these math problems, or at least in this particular work. I know you've also looked a little bit into the ability for LLMs to speak about graphs. Could you share some details about CoCoGen?
So CoCoGen is this paper that Shuyan and I did last year and a half ago. And the idea was that if you are doing structured common sense generation, by which I mean if you're doing graph generation. For example, if you're given a scenario like generate a plan to bake a cake. Now, this plan can be represented as a graph. So the first node in the graph can be gather ingredients. Then you can have a next node or an event, which is mix ingredients, start the oven, and so on. So you have this directed acyclic graph or a plan. Existing works up until that time, of course, everyone was already using language models for this kind of stuff, right? They were already good. But the question is, how do you represent this output? What structure do you use? The most common idea was to break down this graph into a sequence of edges and then use the language model to generate it. So if you have, there's A to B and A to C, then you have two edges, A, B, A, C, and just generate it. What we proposed is instead of doing all that, like writing the graph as a string, writing it as sequence of edges, why don't we represent the graph as a Python class? So there can be a fake class, bake a cake, and it could have fake functions like gather ingredients, mix ingredients, start the oven. And the dependency between these events or the edges is again very natural. You can write a main function, and the main function can call these fake events in the right order. So I keep saying it's fake because we don't really care about the Python class itself. Python is only a way to represent the structure. That's our CoCoGen work, which sort of set the stage for some of the other follow-up works. Like PAL is, I think, the most noteworthy. Mm-hmm. Yeah.
And then is there anywhere listeners can follow you online?
I'm on Twitter. My Twitter handle is SHUYANZHXYC. And also my homepage is myphonename.com, shuyanzhou.com.
And I think for me, my Twitter is just my first name _ my last name, just much easier than Shuyan's. But I think if you find either of us, you'll find the other because we have a lot of work together. And also, I have a website, which is my lastname.github.io.
Cool. We'll have links to all of the above in the show notes for people to follow up with. Thank you both so much for taking the time to come on and share your work.
Thank you so much.
Yeah, thanks a lot for talking to us.